guys, we're gonna quickly go over some like standardized test style questions for fluids. I've just grabbed some things out of some books, so we'll just kind of see how it goes. Um, we're not gonna do every problem on every page that I've looked at, but we'll do a few. Just kind of bring some of these ideas together. We're gonna look at number 6 here. It basically says that we have fluid that's flowing from left to right, say water, and it's flowing through a pipe that has different segments of different diameters. And on top of each of these segments, there is a vertical pipe that's presumably open to the atmosphere, and each of these is going to have a certain level of fluid inside of them. And they're asking which of those pipes, 1 through 4, is going to have the lowest level of fluid. So if it has the lowest level of fluid, that means that the pressure underneath that fluid stack would be the lowest. So we're looking for the region of pipe where the pressure is going to be lowest. Is it the region underneath 1? Is it 2, 3, or 4? So they're asking us to combine the continuity equation, which says that as pipe size diminishes, fluid velocity increases, with Bernoulli's principle, which says that as the velocity of the fluid increases, the pressure of the fluid in that region diminishes. And so if you put those two concepts together, that means that the faster a fluid is moving, the lower pressure it has, and the faster fluid is moving, the more likely it is to be, well, it's going to be in a very small region of pipe. I'm going to choose the smallest diameter region of pipe, which is this one here. That's where the fluid is moving the fastest, which also means that's where the pressure is the lowest. Which means that the fluid stack that pressure is able to support is going to be smaller than all the other pipes. So B is the correct answer there. Next question has to do with something that we've talked about in the last video a little bit, and I'm not going to belabor it too much. It's just to say, why on earth is blood flow so much less in the capillaries than it is in the aorta if the continuity equation says that as pipe size diminishes, fluid velocity should increase? So biologically, that's not the case with capillaries. And we talked about how there's a lot of reasons for that. The viscosity becomes important. The fact that blood isn't an ideal fluid at those really small scales is also important. But the final thing is that there's so many capillaries that if you were to add up all the cross-sectional area of all the capillaries, it would dwarf the aorta. And so because a given capillary has a flow rate that is so small, we expect that the fluid velocity would decrease there. So if you took all the capillaries and you bundled them together and you compared them with the aorta, effectively what we're saying is it's natural to think that the fluid velocity would slow down through that region, that bundle, if you like, of capillaries. And so I'm going to put C here because that expresses that idea. The cross-sectional area of all the capillaries added together is so much greater than the cross-sectional area of the aorta. Okay. I'm going to just do number 10 here. These other questions are interesting, but we're just going to skip to number 10. So this is a hydraulic system. So presumably what happens is here on this first piston we apply a force. And the question is what force needs to be applied on the other end to balance the system? So the principle we're using here is Pascal's principle, which basically says that the pressure over here has to be the same as the pressure over here. Really what Pascal's principle says is that a change in pressure is transferred undiminished through the whole fluid. And so a delta P here has to be the same as a delta P there, is the way our logic is flowing. So what they're saying is we're putting down 4 newtons of force over here, and the area over here is 16 in whatever units it is. Well, I know what the area is over here. It's 64, so that's a factor of 4 times the area on the second piston. The question is what force do I have to push down on the second piston to match that difference in pressure? Remember that pressure is just force divided by area. So let me just write that here. And so if the area has increased by a factor of 4, that means that the force is going to have to increase by a factor of 4 as well to keep up. So I'm going to look down here and see if there's an option like that. 4 newtons, here it is. And we'd be done with the problem. Okay. All right, I have another set here. we'll just kind of quickly go through these ones here as well. So this question says, if the container pictured below is filled with an ideal fluid, that means we don't have viscosity or funny business acting, at which point in the fluid is the pressure most likely the greatest? So, that's a good question. I know it's not A, pretty sure, because A is at atmospheric pressure, and at other points in this fluid, there's fluid on top of those points, and so it'd have to be bigger than atmospheric pressure. I also know it's not D, because D is also at atmospheric pressure. It's out in the open. So it's a contest between B and C. Remember that Bernoulli's principle, though, says that the faster a fluid is moving, the slower the pressure. We can ask ourselves, where is the fluid moving the fastest in this apparatus? Is it moving faster here while it's sitting in the tank, or is it moving faster here as it's preparing to exit? And I would argue that it's moving faster at C. And so if it's moving faster at C, that means the pressure is lower there, so B is the correct answer for that one. Alright, and I might not do any of these here. We're gonna move up the chain here. This is one that I wanted to look at, kind of using the same idea. So we have a tank of water or some other substance, and the spigot is some height h from the top of the level of fluid, and the spigot is 1/4 h above the ground. It's going to ask us some questions. So the first question is if the container is filled with water and h is 20 meters, that's tall, 20 meters, then what is the pressure at C? And this is a trick question, because where is C? Is it inside the tank? No, it's right at the edge, and it's open to the atmosphere, so we say 1 atmosphere, and we'd be done with that problem right off the bat. The next question says, if the container is filled with water and h is 20 meters, what's the velocity of the water at point C? So what we're going to do is we're going to use Bernoulli's equation, which is kind of a energy conservation equation, to try to figure this out. So we have this much potential energy in fluid weight, if you like to think of it that way, on top of that spigot there. And then all of that weight's going to be converted into kinetic energy by the time the water enters that spigot, because no fluid will be on top of it. So what we're going to say is, okay, what I'm going to say is that rho g d, which is potential energy for the fluid, is going to be equal to 1/2 rho v squared. And I'm going to solve for v. I'm going to convert all of that potential energy into kinetic energy. So notice that the density of the fluid goes. It doesn't matter what the density of the fluid is. And we're going to say, okay, so then v is equal to 2 gd, root 2 gd. And so they're saying that if the height is 20, and we know what gravity is, it's 10, so what's the square root of 400? Well, that's 20. I'm going to come up here and see if there's a choice for that. There is. It's right there. I'm going to go ahead and just select that. So again, what we've done is we've basically set potential energy equal to kinetic energy for the fluid to get that answer. Now, if the container is filled with water and h is 20 centimeters, what's the pressure at point B? What's this pressure here? Well, the pressure is rho gd plus an atmosphere. Right? They didn't say the gauge pressure, so I have to calculate that as well. Water is 1,000, gravity is 10 for MCAT reasons, and this is 20. So already I'm seeing that this is 2 atmospheres by itself. Then we add 1 atmosphere to it. That's 3 atmospheres. So we'll go ahead and put 3 atmospheres of pressure there. If the container is filled with water and h is 20 meters, what is the distance d? How far does the water reach out? Well, that's a projectile motion problem. How far does a ball land from the base of a cliff if it's thrown horizontally at 20 meters per second? So I'm going to try to do this as quick as I can using a kinematic. How long does it take water to fall 5 meters? So we're going to say, okay, y final then is going to be equal to, let me change pen colors here, it's harder to see. Y final is equal to 1/2 gt squared. Kind of simplify the kinematic equation there. So y final is 5 meters, you need to fall 5 meters. And that's equal to 2 times 10 times t squared. You can see that this is all going to cancel out. So I'm going to get 1 is equal to t squared, so t is equal to 1 second. Man, they may have designed this that way. So we have 1 second of fall time. How far horizontally can a ball thrown at 20 meters per second move in 1 second? Well, it can move horizontally 20 meters in 1 second, let's say, and so then we'd be done with the problem. If the distance d were 10, say, and it was filled with water, what would be the distance if it was filled with mercury? And this is kind of an interesting question. Would you imagine it'd be more than or less than if the fluid changed? And this is somewhat counterintuitive, but you know, looking at the exit velocity here, notice that that is independent of what the density of the fluid is, because yes, even though there's more weight with the mercury, it also takes more effort to accelerate mercury, and so the two effects cancel exactly. So it actually doesn't matter. The mercury is going to be leaving at the same velocity, and so we're going to say 10 meters, and we're going to call it good. We're done with that. All right. If the pressure at B is 2 atmospheres, okay, here we have 2 atmospheres of pressure now at point B, and the container is filled with water, what would be the pressure if the container were filled with mercury? So, all right. So basically there's one, where do those 2 atmospheres come from is the question that they're asking pretty much. So there's 1 atmosphere that comes from above, and there's 1 atmosphere that comes from the fluid. So changing it to mercury would not change the atmosphere's contribution. So we're going to set that aside. But it would change this contribution here. Mercury is about 13 times heavier than water, 13.6, so almost 14 times heavier than water. And so I'm just going to multiply that by 14-ish, 13.6. We're looking at something around 15 atmospheres. 14 plus 1 atmosphere from the top. And there it is, right there, 14.6 atmospheres. You get 13.6 atmospheres from the fluid, one atmosphere from the top. So finally, if the velocity at C is 2 meters per second when the container is filled with water, what would be the velocity if the container were filled with mercury? And again, yes, there's more weight that's pushing down with the mercury, but it also takes more pressure to accelerate it. And so again, the two effects cancel each other exactly. So they give us a lot of interesting information here we didn't need. So I'm not sure if that was helpful. Probably wasn't. But anyway, for what it's worth, thought I would show you a couple of fluid dynamics style problems in sort of a standardized test context. And in the case, that was helpful. So anyway, thanks for watching. We'll meet up next time, I guess.